This video will demonstrate the major improvements in integrated 12.0 programs by breaking them up into geometry, physics, and analysis. Geometry. In all our 3D programs, you can now project points, segments, and surfaces onto arbitrarily shaped surfaces in a specified direction. The process is intuitive. Simply select the appropriate geometry entities, points, segments, surfaces. Choose the target surface, and input the projection direction. This model is the outcome of projecting a square surface onto a spherical surface in the direction of x equals -1, y equals 0, and z equals 0. For surface projections, you even have the option to retrim to eliminate overlapping surfaces. This command can be utilized for many purposes, like creating a new volume by joining these two patches on the surfaces using define volume from toSurfaces command. Another new command is the spherical cap creation command. It is shown here how it can design seamless junctions between cylinders and spheres with matching or larger radii. This is especially useful in designing of models like corona rings. You can also change the size of an arbitrarily oriented arc and circle using Scale Arc and Circle command. After selecting the circular arc segments or surfaces, the only user input is the scaling factor. Physics. The model tree contains mesh and study branches now, which can be expanded and collapsed using the control that toggles between expand and collapse states. Many operations like editing mesh settings, mesh weight, and solver settings can be performed by right-click from the mesh and study subbranches. You can now create definitions that are more readily seen and edited than in past versions. And there are new options such as maximum element size. You can now select multiple physics objects of the same kind in the workspace, and use one of the right-click menu options to operate on all of those items concurrently. For example, if you have several current sources as shown that you want to reverse the direction of, you can use Ctrl+click and Shift+click to select the current sources in the workspace, and then right-click. The options available for operating on multiple objects are given in the right-click menu. The magnetic branch of the physics menu in magnetic programs has major feature developments to model magnetic materials and applications. Version 12.0 of magnetic programs have a new feature to model anisotropic materials now. Right-clicking on Anisotropic command in Physics menu will open the Anisotropic dialog box, where you can set the direction of anisotropic materials. Electromagnetic simulations of the device or equipment, which has laminated parts, may be performed using a new feature in magnetic programs. You can find this feature under the Physics branch in the model tree. By specifying the volume orientation, stacking factor, and number of sheets in the model, laminations can be simulated efficiently. Another new feature is an improvement in the permanent magnet dialog box. For an arbitrarily oriented permanent magnet part with the direction of magnetization corresponding to the direction of orientation, the direction vector of the magnet may not be known or easily determined. In this case, it may be more convenient to select 2 points, either on the part or on some reference geometry, to define the direction of magnetization. Two-dimensional magnetic programs have new parameter to calculate the total power loss per unit volume in magnetic materials when subjected to external sinusoidally varying magnetic flux. This can be calculated from the material table. You need to enter Steinmetz model parameters as you see here. Then, after solving the model when you request for magnetic power loss in the field, results, you will see the results. The trajectory, physics in Lorentz, now follows the same structure and options as other physics types. The definitions behave more like voltage, current, permanent magnets, etc. In addition to the existing particle beam option, Lorentz now has a particle bunch option. Under the Geometry and Solution dialog box, for beam analysis, the basic emitter types are still preferred. However, using the new advanced emitters, you can set up various bunched emitters and use some new analysis options specific to bunches or pulses to study effects like the Borch effect in 3D and to more clearly identify pulsed behavior with quasi-transient analysis in either 2D or 3D. Many operations can now be performed by right-click from the trajectory title in the model tree. One can now add point, segment, and surface emitters with basic and advanced settings by right-clicking on those subbranches. There is now a new segment and surface emitter type, which is particularly useful for setting up current pulses or bunches. Analysis. Lorentz now has the option to use a slider to animate some analysis. In this case, one can create beam plots by using a slide to choose plane. Instead of making a lot of individual plots along the beam axis, use the slider to see plot updates live as you pick locations along the axis. Users of a 2D program now have the ability to view their model geometry in 3D. The 3D view mode includes the Standard Views toolbar, enabling users to set different standard views and shading options. Additionally, users have the flexibility to pan, zoom, and rotate their views in 3D. Zooming in on points in a graph results in zooming in with the axis changed to reference the area that is zoomed in on. In some cases, you may want to calculate a field on arcs or circles and compare the field as a function of angle. To do this, you may create several arcs to calculate the field on. When you create the individual graphs on these arcs, the default graph display makes the distance along the curves the default abscissa x-axis for the graph. This may not be helpful for comparing field values at the same angle. If you want to change the abscissa to angle relative to the arc center, right-click in the graph area and select Graph Properties from the pop-up menu. This opens the Rectangular Plot Properties dialog. Select the X-axis tab to view the X-axis properties. Then, change the X-axis quantity to angle to scale the abscissa according to angle rather than distance. When finished, click OK, and the graph will be displayed with angle as the abscissae.